For a long time, Venus felt familiar. It is almost the same size as Earth, almost the same mass. It shows up regularly in the sky, bright enough to catch your eye even if you are not looking for it. From far away, it looked like a planet that could have taken a path similar to ours. Early telescopes could not see its surface. Venus is wrapped in thick clouds that reflect sunlight and hide everything below. That blank canvas invited imagination. Some scientists pictured shallow oceans. Others thought of rainforests or swamps, warmed by constant sunlight. Even into the mid-20th century, the idea that Venus might be habitable did not sound unreasonable. Then the Soviet Union decided to stop guessing. During the height of the space race, while much of the world focused on the moon, Soviet engineers aimed for a harder target. They sent probes toward Venus, knowing most of them would fail, and many did. They were crushed, overheated, or lost contact minutes after arrival. But a few survived long enough to send something back. What they returned was not speculation or theory. It was direct measurement, real numbers, real images. Data taken from a place no human-made object had ever reached before. Those signals told a story that no one expected. Venus was not a slightly warmer Earth. It was not a planet that missed being habitable by a small margin. It was hostile in a way that forced scientists to rethink what Earth-like even meant. The discoveries made by those Soviet landers did more than describe Venus. They changed how we think about planets across the entire universe. They showed how two worlds can start out similar and end up completely unrecognizable. From Earth, Venus gives very little away. Telescopes show a smooth, bright disk with no visible surface features. That is not because the planet is simple, it is because its atmosphere is so thick that it hides everything below. For a long time, that ignorance worked in Venus's favor. Before spacecraft, astronomers relied on reflected light, orbital motion, and basic physics. Venus is close to Earth in size and density. It formed in the same region of the solar system. It receives more sunlight, but not an absurd amount more. On paper, it looked like a slightly warmer sibling, not an alien world. The clouds were the biggest wild card. No one knew what they were made of or how thick they were. Some scientists assumed they were water clouds, similar to Earth's. Others imagined constant rain, maybe shallow seas underneath. Because Venus rotates slowly, people even speculated about a planet with one side in daylight and the other in night, creating strange but potentially stable climates. Radio measurements in the 1950s added confusion. Early data suggested Venus was warm but not catastrophically hot. Depending on how the numbers were interpreted, the heat could be coming from the atmosphere or the surface. Without direct measurements, both ideas stayed on the table. There was also a psychological factor. After discovering canals on Mars were an illusion, Venus became the next hopeful candidate for life. It was closer, brighter, harder to rule out. In an era with limited data, similarity carried a lot of weight. By the time spacecraft technology matured, Venus was not just interesting. It felt unfinished, a planet that demanded a closer look. The only way to settle the debate was to go there and find out what was hiding beneath those clouds. Landing on Venus was never a gentle idea. Soviet engineers knew this early. Calculations showed crushing pressure, extreme heat, and an atmosphere dense enough to tear spacecraft apart on the way down. Still, the Venera program moved forward, mission by mission, learning from failure in a way that feels almost brutal. The early probes barely made it into the atmosphere. Some lost contact during descent. Others were flattened before reaching the surface. Each failure answered one question and raised another. The pressure was higher than expected. The temperatures were climbing faster than predicted. The atmosphere was not just thick, it was aggressive. Instead of giving up, the designs became tougher. Landers were built like armored vaults, spherical pressure vessels, minimal moving parts, electronics packed inside insulation, with no expectation of long survival. These were not explorers meant to roam. They were built to endure just long enough to speak. Parachutes slowed the descent, but even those became a problem. The atmosphere was so dense that some probes drifted too slowly, overheating before they could land. Later missions ditched parachutes entirely, dropping faster to buy time on the surface. When Venera 7 finally transmitted data from the ground in December 1970, it changed planetary science. It proved that landing on Venus was possible. Not safely, not for long, but possible. Later missions pushed further. Some survived over an hour. A few even sent back images. Every success came with a clock ticking loudly in the background. Engineers knew exactly how little time they had. That urgency shaped everything the probes did, and everything they revealed once they touched down. When the landers reached the surface of Venus, the numbers came in fast, and they were unforgiving. Surface temperatures hovered around 460 degrees Celsius, hotter than a self-cleaning oven, hot enough to melt lead. Whatever Venus once was, it had crossed a line long ago. The pressure was just as shocking, about 90 times Earth's surface pressure, comparable to being nearly a kilometer underwater in Earth's oceans. The landers were not sitting on the ground so much as being crushed into it. This explained why earlier probes failed so quickly. They were simply not built for a world like this. The atmosphere told another part of the story. It was mostly carbon dioxide with clouds made of sulfuric acid. Not steam, not water droplets. Acid. The sky was thick and yellowish, scattering light so heavily that shadows were faint or missing entirely. Daylight existed, but it was dim and diffuse, more like a permanent overcast than a sunny day. Then came the images. The first photos showed a flat, rocky landscape scattered with angular stones. No signs of erosion from water. Most sand dunes shaped by wind in the way scientists expected. The rocks appeared basaltic, similar to volcanic rock on Earth. That hinted at a planet shaped by lava, not oceans. Chemical sensors backed this up. The surface composition suggested widespread volcanism in Venus's past. A planet that likely released enormous amounts of gas into its atmosphere over time, trapping heat more efficiently with each passing era. Together, the data painted a clear picture. Venus was not merely hot, it was locked into a stable, extreme state. A planet where the atmosphere dominated everything, and where the surface existed under constant crushing punishment. Once the data was in, Venus stopped being a mystery planet and started becoming a lesson. The conditions measured by the Soviet landers were not random. They pointed to a specific process that had run to completion. At some point early in its history, Venus may have had liquid water. Models suggest it could have been warm, not extreme. But being closer to the sun mattered. As temperatures rose, more water vapor entered the atmosphere. Water vapor is a powerful greenhouse gas. That trapped more heat, which evaporated more water, which trapped even more heat. The process fed on itself. Eventually, the oceans would have boiled away. Ultraviolet radiation from the sun then broke water molecules apart in the upper atmosphere. Hydrogen escaped into space. Oxygen reacted with surface rocks. Once that happened, Venus lost its ability to cool itself. There was no easy way back. Carbon dioxide piled up next. On Earth, carbon dioxide cycles through oceans, rocks, and living systems. On Venus, with no liquid water and no plate tectonics like ours, it stayed in the air. Volcanic activity likely kept adding more. Over time, the atmosphere became a thermal blanket that nothing could escape. What made this unsettling was how ordinary the starting point seemed. Venus did not need a rare event or an impact to end up this way. Just a few differences in distance, chemistry, and timing were enough. The result was a planet locked into a runaway greenhouse state for billions of years. That realization changed how scientists think about planets beyond our solar system. Similar size does not mean similar fate. A planet can look familiar from afar and still be completely hostile once you step onto its surface. The Soviet missions to Venus did not just explore a planet, they closed a chapter of guesswork that had lasted centuries. After Venera, Venus was no longer a blank world hidden behind clouds. It was measured, photographed, and understood on its own terms. What stands out now is how final those findings were. Venus is not slowly drifting toward habitability or waiting for the right conditions. It has settled into an extreme balance that reinforces itself. Heat creates pressure. Pressure traps heat. The atmosphere dominates everything below it. Once that loop locked in, the planet stopped changing in any meaningful way. That makes Venus powerful as a comparison. Earth and Venus likely started with similar ingredients: rock, water, carbon, sunlight, but small differences compounded over time. One planet developed oceans, weather cycles, and life. The other lost its water, sealed its atmosphere, and turned its surface into a furnace.